In order to find the forces in roof truss members CD, CF, and GF, we can utilize a method of section. So in method of section, what we do is basically cut those three members and separate the truss structures into two portions. Now we can select any one of those portions to do our analysis. Typically we pick a portion that have least amount of unknowns on it. So if you see in the right hand half of the portion, I have just one unknown, that is my roller support. So let's go ahead and solve for this roller support first, and then we will do the analysis on the selected members. So to start, we have to develop our free body diagram. I'm just going to draw the support reactions on the image itself. So here at A, I have a pin support that will have a force AY and AX, whereas for the roller, I have only one vertical support going in the upward direction given as EY. Now once we have that, we can apply our equilibrium conditions to solve for the support EY. Now if you look, if I apply the summation of moment at point A, both the unknowns AY and AX won't create any moment, and the only unknown load will be of EY. So let's go ahead and apply that equation. Here I have an external load of 2 kilonewtons that have a moment arm of 0.8, and that is going to create our clockwise moment. That's why we have it as a negative. Similarly, I have an external load of 1.5 kilonewtons having a moment arm of 1.7 plus 0.8, and that is also creating our clockwise moment. And in the end, I have this support reaction of EY that has a moment arm of 4 meters, and that is creating our counterclockwise moment. Simplifying, we get the value of EY as 1.3375 kilonewtons. Now once we have the support reaction of the roller EY, let's go ahead and apply our method of section. Since we are interested in the members CD, CF, and GF, we need to apply our cut along these three members, and in this case we are going to pick the right hand portion of this cut. So to do that, let's start developing our free body diagram. And here I have my E, F, and D portion, whereas next is a member going from D to C. In this case, that will be cut. So once we have made a cut, there will be internal load that will become exposed. Since truss is a two-force member and the load only act along the axis or the direction of the member, so we will just have the force going in the same direction. Now by convention, we pick the load in the tension direction, and based on our calculation, if we get a negative number, we can identify that as a compressive load. Next, I have a support reaction at E going in the upward direction of 1.3375 kilonewtons. Now, once we have this, we can go ahead and start applying our equilibrium equations. We can start with the summation of moment at point F equals to 0. Since if I pick summation of moment at point F, the forces FCF and FGF, as they are passing through the line of action of point F, they won't create any moment, and we will have just the one unknown FCD. Now in this case, the moment arm of FCD is the variable X shown in the free body diagram. So we have to calculate that value of X here. Next, we have our force at the support E that have a moment arm of 1 meter that is creating our counterclockwise motion. Now once we have the equation, let's first figure out the value of X here. Since we are given the length from D to E as 0.8 and from F to E as 1 meter, and since it is a right angle triangle, we can calculate our value of X by using the Pythagorean theorem. Here the value of X is coming 0.36 meters. Now, once we have this value, let's plug it back into our expression and solve for FCD. And here the value is coming as negative 2.23 kilonewtons. Now, one thing to point out, since we are getting a negative number and we have picked in our free body diagram the direction of the force in tension direction, so it is identifying that the force in the member is in compression. Next, we can go ahead and write our second equilibrium equation. If you look at the free body diagram, I have three loads that are going through point E. And if we write the summation of moment across this point, those three forces won't create any moment as they are passing through the line of action. So we will have only our force F of CF that will contribute to the moment. Now in this case, I have two components of the force. One is the vertical one and the other one is the horizontal. We can identify those two components by using the information from the triangle. So since the base is 1 meter and the height is 1.5 meters, again, utilizing the Pythagorean theorem, we can identify the hypotenuse of this right angle triangle that is coming as root 3.25. Now, if you look at the two components of the force in CF, the horizontal component force line of action is going through point E and it won't create any moment. So only the vertical component of this force is going to create a moment. So to write that vertical component, I can multiply FC of F by 1.5 divided by root 3.25. In this case, the moment arm is 1. And since this is the only force that will create a moment across point E, its magnitude will be equals to 0. Now, finally, we can write our summation of forces along the horizontal direction equals to 0 and solve for our third unknown, that is force in the member GF. Since the force in the member GF is directed to the left, here it is taken as negative. Next, I have that horizontal component of the force in member CF. Since its magnitude is equals to 0, there won't be anything there. Finally, we are left with the horizontal component of the force in member CD. Again, utilizing the triangle dimensions, here we have our 3, 4, 5 triangle ratio. We can calculate the horizontal component by multiplying the force FCD with 2 divided by 2.5. Now plugging in the value of force in member CD as negative 2.23 kilonewtons, we can solve for the force in member GF. Now one thing to point out here is we need to be consistent. Since I was getting a negative value, we need to plug in the negative number in this expression to be consistent with our free body diagram directions. Now plugging it in, we are getting a force in the member GF as 1.78 kilonewton, and since I'm getting a positive number, the force is in tension.